For those very long questions, feel free to track me down later. So for this audience, I don't really need to go through my usual background slides, but I'll just go through a few really quickly because I will be talking about the Fiori bursts. And just very quickly, as you probably know, that is one supposed phase of the young stellar object's evolution during which the luminosity, and by implication the accretion rate, rises to 3 or 4 orders of magnitude above the standard T-Tauri star accretion rate. So you go from about 10 to the minus 8 to minus 7 solar masses per year, up to about 10 to the minus 4 solar masses per year. There's only about 24 of these objects that have been detected, and here's the light curves for a few of them. They all look different, but the basic point is a rapid rise, and then a decay time, which is on the order of decades. So you can expect by a century maybe to have gone back to the pre-burst state. And this is Fiori itself in optical light. Typically there is a nebulosity that you can detect around these sources, implying that there may still be mass accumulation going on from the surroundings. So these statistics of the Fioris led Lee Hartman many years ago to essentially make a hand sketch of what YSO accretion history might look like. And again, based on statistics, even though, as I said, there's not a very large number of these objects detected, even that is quite large compared to some estimate you might make if every low mass star within the distance you could reasonably expect to see them underwent even one burst in its lifetime. So the implication is that probably each YSO early in its life would undergo multiple bursts. Canonical number is 10 to 20. And then it would later on settle into a more stable disk accretion state. And Lee had sketched in a dashed line representing the infall from the envelope. And that's, again, by just empirical inference that that envelope that you could see might be driving the bursts. And when the envelope is gone, you settle down into a more steady but still flickering accretion rate. Let me then, from a theoretical point of view, just again do one really quick slide about the Q parameter. Not much more need be said about this, but I'll emphasize here that while this is a stability criterion for a rotating disk, one should keep in mind a few subtleties, and that is, yes, certainly if Q is less than 1, you expect vigorous gravitational instability in your disk. And if Q is much larger than 1, you expect stability in which fluctuations are washed out by thermal pressure and shear. But there can also be an intermediate regime where you're hovering around Q equals 1. You may not be vigorously unstable, but you can still have significant non-axisymmetric structure in the disk. And particularly in this phase, and even here, we should keep in mind that fragment formation, that is, if you have a perturbation that's initially unstable, for it to go all the way to a very high density, you need to worry about the heating and cooling in the disk, as several people, many people in the audience have pointed out. Ultimately, you need the cooling to be rapid enough to let the fragment go to a certain stage. But also, as Edward Vorobiev and I have pointed out, you have to think about that mass deposition on the disk. So even if the cooling criterion is not too favorable, you can get some structure initially simply by decreasing the Q parameter by raising the surface density. So what are our models about? Just a brief synopsis. We are using finite difference code to evolve the evolution of a disk ultimately, but that's not our starting point. Our starting point is a pre-stellar core. So the size of the region that we're modeling is of order 10,000 astronomical units. So we approach this problem from the star formation side of things. We're interested in how a pre-stellar core forms a star and how the mass is accumulated in the star itself. So that's our outer boundary. So we have a global model, certainly for the disk. The disk, when it forms, is occupying 1/100th of our computational grid. And we can resolve that because we have this non-uniform logarithmically spaced radial grid. And it's r and phi, so we're allowing for non-axisymmetric motions. And we are calculating the self-gravity of the disk all along. We are having a disk-like, a thin disk approximation from the very beginning. So our prestellar core is modeled as a flattened object to begin with, and that saves us a lot computationally. It's, in my opinion, a very nice way to be able to solve a large part of the problem, because we have such large dynamic range of space and time that we have to cover. If you can make this simplification, which we do, integrate in the z direction, assume hydrostatic equilibrium, and then solve the time dependence in r and phi, our initial conditions are that of a prestellar core. We've done many models, many people have done models which suggest you're evolving towards some power law profiles in the prestellar core. So we start with those. So really, what's unique about this model? I'd say the strength of it is that not only we have the spatial resolution of going from the outer boundary down to an inner sink, which is at about 5 AU. Outside the sink, we have very fine spacing of our grid, so the resolution might be 1/10 of an AU, just outside the sink. So we had the spatial resolution covered, but even more importantly, we can cover a larger dynamic range in time. So we can form a protostellar disk, maybe 100,000 years after the prestellar core starts evolving, and then follow the evolution of the circumstellar disk for millions of years. So I think that's where we, right now, we win with the thin disk, whereas if you're trying a three-dimensional simulation, typically people are having to stop at around 1,000 years after you form the central stellar core. And as you'll see, if you need to really get to 10 to the 4 years to get the bursts, and you need to get to a order 10 to the 5 years to study the residual disk accretion, the T-Tauri phase that we all know. Finally, because it's thin disk, we can run many, many simulations. A typical simulation may take 2 weeks to run, and we can do large parameter studies. So that's nice. Those are the strengths of the model. What are we not including? Well, this is one laundry list. Maybe there's more you can point out. But basically, we don't have many of the magnetic effects. We can put in a flux-frozen magnetic field without magnetic braking. It adds an extra pressure, and we've done that in some models. That changes the solution quantitatively, but not qualitatively. So I'm not going to talk about that today. But magnetic braking, ambipolar diffusion, other non-ideal MHD effects can come into play at some point. Magnetorotational instability could not occur in a thin disk model if it's driven by if the MRI is driven by the colloidal field. And because we have that inner sink, we are then not modeling the physics inside the sink. And that's as small as 5 AU that we can place the sink in our models. Stellar radiation, radiative transfer, essentially we bypass that by using a pressure density relation that's based on other radiative transfer calculations. Okay, now one nice thing, I guess, one nice light you can put on not having some of these effects is that we do have the sink at 5 AU or so. And many of these effects are expected to become particularly important within that radius. So looking at the schematic from Armitage, Fluvio, and Pringle, you've got some sense that self-gravity is important outside several AU, and within that you start to look at other effects. And certainly it's harder to, well, I'll be talking about the self-regulated phase where Q is held at the critical value. That's hard to maintain all the way in to the central star, as you surely know. Basic equations, quickly, we have these vertically integrated equations. So we have mass continuity for the surface density. We have a momentum equation. And the P is the vertically integrated pressure, actually. And so here's our barotropic equation of state, which transitions from isothermal to something quasi-adiabatic at some critical density. And self-gravity is included. This is, again, remember, self-gravity of a non-axisymmetric system. And yes, we use this very nice method of colonize that's described in Binney and Tremaine, which will allow you to solve for the potential of an isolated system.
Sorry, what's the motivation for being more isothermal at larger surface densities?
At lower surface densities. Okay, yeah, that's the in prestellar cores you have a wide range of densities where temperature is approximately constant. There's a lot of dust emission. Okay, so for prestellar cores, what's our initial condition? Essentially, you know, these are really simpler than they look. Essentially, this surface density profile is asymptotically going as r to the -1 with some central flat region, and these angular velocity is really doing the same, despite looking more complicated. So we have parallel profiles, and we have characteristic rotation. That's your typical molecular cloud velocity gradient. We have, again, our outer boundary at about 10,000 AU. Our central flat region is something smaller. It's essentially a prestellar core model. And again, the nice thing is that we can start from that, build up the central core, then build up the disk around it, and then study the disk for a few million years afterward. I will point out that we've tried other profiles, and essentially you'll get the same qualitative results. Quantitatively, you know, if you pack in a lot more angular momentum, your disk will form earlier and it'll be bigger, et cetera. The basic, you know, our signature result, I guess, is that when you do form the disk, this is picking up the evolution after the disk is formed. Okay, so this is a stage where we've zoomed in on our grid. This is 200 AUs. Remember, the boundary is at 10,000 AU. So this is a small part of the computational grid. The black region is just lower density than the color table allows, so it's not empty. You have matter being fed onto this high density disk. The red is the sink cell, and this is the accretion rate onto the sink. And the basic result is that when you do form the disk, early in the history, you're getting strong gravitational instabilities. Spiral arms form, the arms fragment into clumps, and the clumps are very efficiently torqued in through their interaction with the trailing part of the arm. And when the clumps fall in, you get this big burst of mass. Essentially, you have about 10 Jupiter mass clumps falling in over a period of 100 years, and that's your 10 to the -4 solar masses per year accretion rate. So this happens episodically, not periodically, although there is a characteristic time scale, but that depends on various inputs. The basic, what I want to emphasize is the basic qualitative result, that you do get bursts, and it's very hard to avoid the bursts. They're quite robust. You can change the number of bursts with different initial conditions, but you inevitably will have them because even if you have a relatively hot disk, you have feeding from the envelope. So early on, you can't really avoid the bursts. The previous animation was one of our first attempts at making an animation, and that was a simulation in which we had imposed an m = 2 symmetry in the initial conditions, and you may have noticed that in the movie. Realistically, what happens is you have little perturbations coming up from the calculation at all times, if nothing else through your potential solver, and that maybe mimics a more realistic situation. And so these perturbations lead to different modes being excited. And the most standard outcome is more like this. This is from a simulation where there's no m-fold symmetry perturbation put in initially. Okay, so it's circularly symmetric actually, but little perturbations build up once you get to the disk stage. Before that, it's just monolithic collapse, and it's very hard to build up structure. But you can see again, this is in the early phase, you're typically getting irregular patterns, but there seems to be some dominance of the m = 1 mode.
Can I ask you a quick question?
Yes.
If you start with an incredibly slow rotation, do you still see the spiral structure? Yes, I'm asking because if it's rotating very, very slowly, you shouldn't really form a disk at all. But you're starting
Yes.
with this 2D
Right.
R5 structure in the beginning.
Right. Well, to answer your question, we've studied various rotation rates and always seen the disk in spirals, but we've never had such a low rotation rate that you wouldn't form a disk at all.
See, okay.
Okay.
I see that, yeah.
Okay. Here now is, again, a big part of the story. If you had to put it on two slides, it would be that movie slide and this one. This is the mass accretion history, as we saw it building up in time before. This is the mass accretion onto the sink for the first 50,000 years. Calculation actually goes further. But you can see there's multiple bursts. They're more frequent initially, and then as the envelope accretion declines, they're less frequent. Again, you're talking about peaks that are of order 10 to the minus 4 to 10 to the minus 5 solar masses per year. The floor is at about 10 to the minus 7 or 8. And I'll show you a log-log plot later where you can see that better. Interesting that you can essentially make a connection of the disk accretion with the let's say the spherical or disk-like star formation accretion calculations that have been done for years. Frank Hsu has a famous solution for the singular isothermal sphere where, if you have infall of an isothermal gas, you expect just on dimensional grounds alone, the accretion rate would go as the isothermal sound speed cubed over g. Other models essentially reproduce that scaling, but with different constants. And here, before the disk forms, we are settling into that rate. At some point, the disk will form. The disk forms here when the centrifugal radius of an infalling mass shell is larger than our sink cell, which could be 5 or 10 AU. In reality, of course, the disk would form even earlier. The time here is delayed by the size of our sink cell. So actually, this phase may be very, very short. And as soon as the disk forms, you go down to a much lower level, but you're punctuated by the bursts, so that in some sense the average accretion rate may still be very close to what's coming in from the envelope. Now you can show that these are due to gravitational instability by plotting an averaged Q parameter for our disk in red, and essentially you can see the correlation with when the Q parameter gets to somewhere near the critical value, drops below some critical value, that's when you get the burst. And as the burst happens, you're draining surface density out of the disk into the sink. That raises the Q parameter, so you get up to a stable value. And then as the accretion continues from the envelope, you go down to some critical value, and then you have a burst again. And again, it's hard predicting how big an individual burst will be. That's a mini one. So there is clearly a correlation with gravitational instability. We have vigorous instability going on in the disk when the bursts are occurring. This is the log-log plot I promised you. And it actually goes to a much larger time, 3 million years. So again, this is what really is what we can do with the thin disk approximation at this point. It allows us to get the whole accretion history. Again, you'll get a smooth phase until your centrifugal radius is larger than your sink. Then you go into what we call the burst mode. At some point here, we've actually plotted the envelope accretion onto the disk. When that drops to a certain value, the burst mode ends, and now you're in this residual phase. So I think it's important conceptually. You may divide the accretion into these two modes. The boundary may not be very sharp, and it may be different for differential conditions, but essentially I think it's very productive to think of accretion happening in these two modes. So we identify these with the FU-ORIs. Earlier on a slide I may not have mentioned, but I had it written down. We're now even identifying the anomalously low points, perhaps with the very low luminosity objects, the velos, that have been discovered by Spitzer. Okay, let me see if I want to say anything else. Yeah, notice the residual rates are of order 10 to the minus 8 solar masses per year. Again, varies somewhat depending on initial conditions, as I'll show later. A very important another point is that the disk is never as massive as the central star. Okay, one can justify that on many grounds of gravitational instability. Our calculation certainly demonstrates that explicitly. That
How do you define the disk mass? Of course, it's all there in the beginning, right? You have to choose a radius or something.
that's right. Yeah, we're typically picking a surface density threshold of 0.1 gram per square centimeter. Okay, it's a good question. So the protostar mass, again, really the mass in the central sink, rises as the envelope mass decreases. At some point, the disk forms. In this simulation, the sink's at 10 AU. And then the star, the central sink, grows in these steps. Those are the bursts. And again, this is pretty much in line with the empirical constraints that much of the mass of a YSO is built up through these FUORI bursts and is built up in the early phase, what you'd call the class 0 phase, first within a few times 10,000 years of the formation of the central point. So you build up through these steps. The disk is draining mass every time the star is gaining mass, but it never approaches the stellar mass. It's always of order, in this model, 25% of the central mass. So there's a self-regulation in a different way, then I'm going to use it later, in that these nonlinear instabilities create clumps which go into the center and keep the disk mass well below the stellar mass at all times. Just for, you have to keep me honest, I forget things. That's, of course, your rotational parameter beta of the initial prestellar core. And that's in line with what you observe in molecular clouds. That ratio is extremely small, but due to the dynamic range of collapse, you ultimately build up rotational support. This, I think, is a very interesting set of plots, and I'll try and not rush through it too much. These are various profiles of our model, angle averaged, for angular velocity, surface density, temperature, and the Q parameter. This set of figures is during the burst mode, or toward the end of the burst mode even, 0.2 million years. These two are after the envelope accretion has largely subsided. And I think in this late phase, where it essentially is the disk now, evolving due to its own physics without being forced by the outside. At this point, you get this very nice self-regulation, which, again, many of you have studied already with isolated disk models. This is an interesting feature of a nonlinear feature of rotating disks, that you may be able to settle into this state where the Q parameter sort of sticks around at the critical value. Sort of like a convection zone of a star sticks around at the adiabatic gradient. So what's happening here? Let's say that there is some balance that if you go too unstable, then you're either going to create enough energy to heat up the disk, or you will drain matter into the center, and either way you get back toward Q equals 1. On the other hand, the interesting question is why you don't rise above it. Okay, and I'll address that in a couple of slides. You need to have enough fluctuations sticking around to keep yourself at this self-regulated state. And again, I'll come back to that in a bit. But if that's the case, and your angular velocity in the disk, so you can see the disk boundary here, there's a pretty sharp edge in the surface density. That's another key feature of this model, I think. That if you really build up your disk from the collapse of a prestellar core, you're going to have an edge of some kind. I don't know how sharp it would be a priori. And again, you can argue whether that's sharp or not, because it's a log scale. But it certainly is much sharper than any alpha viscosity model would give you. And I'll show you the comparison later. And that turns out to be extremely important. So you've got this edge of the disk, and within that you've got an approximate r to the minus 3/2 profile, which is parallel to the minimum mass solar nebula profile, but actually larger density. Okay, you're 5 to 10 times higher than the minimum mass solar nebula, depending on which version of the MMSN you look up. Now, why is that? Okay, well, if your disk has a rotation profile that's essentially Keplerian, or maybe quasi-Keplerian is right. It's not going to be perfectly Keplerian, but because there is some mass in the disk, but it's following the same profile. And if you have r to the minus 3/2 then in the angular velocity, and you're self-regulated at q equals 1, more or less in every annulus, then if the temperature doesn't vary a lot, which in this model it doesn't vary a lot. I mean, this is a linear scale. Your temperature is going to go from 10 degrees to 50. Maybe you can argue it's 80 due to stellar irradiation at the inner edge or something, but it's going to be in that ballpark. It's not going to vary by orders of magnitude like these quantities are. And so to the extent that this doesn't vary nearly as fast as those two, then sigma would have the same scaling as the angular velocity. Omega is kappa for Keplerian or quasi-Keplerian. So you can actually get this profile. But as I said, it's 5 to 10 times higher in absolute value than the MMSN. Of course, the MMSN is the minimum mass by definition. So again, that's an important point, that in this model you need the non-axis symmetry to get the result. Finally, your angle average profile is this nice power law, but it's the gravitational torques due to the various modes in the system, the non-axis symmetric modes, that is driving this accretion. And so a picture explains it much better. In the early burst mode, within 100,000 years or so, you are episodically developing these very nonlinear arms. When Q is dropping to the critical value, the arms fragment and those clumps get driven in. That's the essence of the burst mode. Now, even in the burst mode, of course, the disk doesn't look like this most of the time. These are near the bursts, and other times it's in a more quiescent state. But in that mode, this is a signature picture. This is when you get clumps from nonlinear gravitational instability. I'm going to distinguish that from gravitational torques later on. And this may be the phase where you form binaries. You know, some people would say giant planets, but leaving that aside, our model can't form binaries because we have this thing stuck at the center. But in a more general situation, as Matthew Bate calculates, you can, if you have a clump that's massive enough, it could push the central object off center, and you could form a binary there.
Excuse me.
Yes?
Can you explain a little bit more how does this burst mode work? In the sense, how does the accretion work? The accretion of the clump. So you start forming the clump at
Yes.
tens of AUs, and then it falls in very rapidly.
Very
Is it
rapidly.
very rapidly?
Yeah, well,
And how does
yeah.
it manage to lose all of its angular momentum?
Well, I think it's simply the interaction, because you've got a pretty nonlinear arm here, and if you consider this part of the arm is rotating much more rapidly than this part, then ignoring everything else, the arm-arm interaction will be that this part of the arm gets torqued in due to getting pulled back by that piece, and that
What's
part of the arm gets torqued out.
Timescale for the accretion of the clump?
I mean, it's happening in thousands or tens of thousands of years. Maximum 10 to the 4. So it's,
Tens of thousands.
no, maximum of 10,000. So it would be thousands of years, essentially.
Move.
Yes. And it depends where you
How does it
are.
fit with, you're trying to use that to match the Furionis outburst.
Right.
How do the timescales fit?
Well, it's a good question. The spacing is, again, it depends on your initial conditions, but the most common spacing that we get is, is somewhere in the thousands. Here it's actually thousands. Here it's more like 5,000 going toward 10,000. So it's, again, between 10 to the 3 and 10 to the 4, or even a few times 10 to the 4 later on. And I think that is about the ballpark for the FU-Ori bursts, by inference, okay? Because you've never seen a single object, right, undergo multiple. But based on the statistics Hartman drew the sketch upon, I think he had a spacing of about 10 to the 4 years between bursts, okay? That's just from the statistics of how many FU-Oris you see versus how many YSOs you expect within a kiloparsec. There could also be many more bursts that happen in the embedded phase that have never been observed. And so I think that's maybe a prediction of our model, that if you could see the very early phase, there'd be many more bursts and much more shortly spaced.
I guess I was going to ask, so presumably you just know that this clump goes inside your 5AU, right? So
yes.
If you were to add tens of Jupiter masses into a few AU, you're going to have surface densities in that inner region of 10,000, 100,000 grams per square centimeter, and you're going to be hot.
Right.
So the real mechanism might be MRI, not the clump actually hitting the star.
You need some mechanism to keep this accretion going through the central.
So you're
AU.
really just saying you put a lot of mass into this inner 5AU, can then
Right.
drain onto the star
Right.
in short time scales.
Right, right. Yeah, you need something else. I mean, in a sense, you're forcing the system, whatever it is inside that 5AU, with this input. And it's either going to go through smoothly or it'll go through in bursts.
Do you know the sort of periastron of your clump, for example? Do you know that it's going to hit the star? You just know that it goes inside 5AU, and of course it can't come back out again because your simulation is left, right?
Right, yeah.
So,
Yeah, no.
presumably it's eccentric, not.
Yes, it's quite sheared too. By the time it gets in there,
So
it's
it's going
sheared
to form
up
a
quite a
disc
lot.
inside there, right?
Yeah, sorry?
Probably going to form a disc inside there, right?
Yes, yes, I think you're right. And then you need, I mean, it won't be a smooth disk, it won't be an axisymmetric disk, and so, yeah, something will have to give. And that's where, I mean, the old picture, some people had MRI forcing thermal instability, right? And now we're saying, well, maybe it's actually fed from out here. So the feeding isn't smooth. Its feeding itself is bursty into the inner region. And maybe that's another way to distinguish between other models where you have smooth feeding from the outside and then something bursty happens on the inside, okay? An advantage of these large-scale driven infall bursts is that you've got this roughly 100-year rise and fall time. So the fall time is okay, okay? The rise time is, of course, much longer, but yes, that's where you need the inner physics to give you the 1-year rise time.
And that time scale is what, just a few orbital times at the inner edge of your
Yes,
boundary?
yes, I think so, right. It's, which time? The
orbital time.
the 100 years, yeah.
5 or 10 years.
Right, right. It's a bit longer than that, I think. Yeah. Okay, now, I think I was somewhere here. The late phase, which we're distinguishing qualitatively, has a much more diffuse spiral structure. You do not have nonlinear, vigorous gravitational instability, but you are still in this self-regulated phase, which you could call it GI if you like, but I think it should be distinguished from the vigorous GI. Certainly, to the extent that you have weak spiral structure, you again have this interaction of an arm with itself, inner regions being driven in, outer regions being driven out. But it's really quite complicated because you have many different high-order modes all interacting with one another. And so you may ask the question as to why such a state could persist for 3 million years or so. Okay, that's how far we did the calculation, and T-Tauri star disks typically survive for at least 3 million years. What's the energy source to allow these even weak, non-axisymmetric fluctuations to persist in the disk for millions of years? So we're not really talking about a turbulent disk, right? there's no vigorous instability feeding in energy. In our models, the surface density fluctuations go from about 10% down to about 1% between the beginning of the self-regulated mode and the end. The fluctuations are actually going away, but slowly enough that there's some residual accretion. The accretion rate is declining with time, but it's in the right ballpark to explain the T-Tauri accretion rates. So the interesting piece of physics is the swing amplifier, which I think holds the key to understanding why the fluctuations hang around as long as they do. The idea is that it's not an instability, but maybe a transient local instability, even though the disk is globally stable or marginally stable. And so Toomre had studied this quite deeply based on Goldreich and Lyndon Bell, and he published this very nice figure in his 1981 review paper, which illustrates the swing amplifier at work for a stellar system, but it can work in similar ways for a gas dynamical system. And the idea is that if you have a rotation, let's say in that direction, and for some reason you have a leading spiral arm, so the direction of the arm is leading in the direction of rotation, then the rotation of the disk will naturally unwind that leading arm into a trailing arm over time. But the key point, this is my limited understanding, the key point is that at some point as you're unwinding from leading to trailing, the arm is in a frame of reference where the, in the gas dynamical sense, where the support due to Coriolis force is locally lost, and you can have a transient gravitational instability, amplification, in some local region. So here, in this case, you can see the amplitude of the arm starts increasing as this thing unwinds into this kind of neutral state, and now you have a much larger amplitude trailing wave, and then over time the amplitude goes down again. And so you get a little bit of boost, okay? It's like someone pushes the swing every now and then, and you get a little bit amplitude put in. But then the question is, why would you have leading waves continually enter the system if their fate is to always be unwound into trailing waves? And so Toomre worried a lot about this, and he was looking for this feedback loop that would keep new leading waves coming into the system so they could be unwound and giving you some amplification. And of course, for galaxies, it's a very difficult problem. I don't know if there is a clear resolution to that question. But in our case, because we have this sharp edge, that helps out a lot. And so our claim is that we are getting the swing amplifier effect because you've got trailing waves that are reflecting off the edge, and a reflected trailing wave is a leading wave. And so the reflections coming back in would give you some transient amplification as they unwound. Now, how much can we prove that? Well, certainly the fluctuations are largest near the edge. And if we do away with the edge with some kind of diffusion, fluctuations go away very quickly, and you're back to an axisymmetric disk. So I think that is a reasonable explanation. It seems, it's not turbulent, but it is this transient feeding, transient instability, if you like, that keeps the fluctuations going. I'm not going to spend a lot of time on this plot, but basically we've done our bit to try and fit an observational correlation between the mass accretion rate and the central object mass for T-Tauri stars and brown dwarfs. This is the observers in this field are always putting up this plot where the m dot seems to scale as some power of the central star or brown dwarf mass, the power that is approximately 2, maybe a little bit less. And over the range that we can fit with our models, we're entirely in the T-Tauri realm. The open symbols are the data points for various stars. The black points are our model averages between 500,000 years and 3 million years. So the average is essentially the average of some range of values, which is what the error bar represents. So if we just plot the averages, I won't push this too far because for a lot of reasons, this is more of an observational correlation, and maybe from a theoretical point of view, it's not the best correlation to be trying to fit. But certainly we get an increase in the accretion rate. You know, I showed you models where the accretion rate was somewhere down here. But if we start with a larger core mass, more angular momentum, we get larger accretion rates at the end. So, so we certainly have an increasing trend, as you might expect, as you start with larger and larger core masses. And that trend, you know, for whatever it's worth, can be fit with some power that's larger than 1. So that's interesting. We're in the right ballpark for the T-Tauri star accretion rates. Even though our disk mass is actually 10 times the MMSN or so, we still have near Keplerian rotation. It's hard to distinguish these profiles from Keplerian because they have the same approximate profile. I think observation, this goes back to a talk David Woolner gave here last month. I mean, it's probably very hard to really distinguish at this level observationally whether your disk mass, based on Keplerianity, is there a new word, or not. It looks a lot like Keplerian, even if your disk mass is about 10 or 20% of the star mass. So this is the big question then. Disk to star mass ratios are bigger, not only than the minimum mass solar nebula, but also than the estimates based on dust emission from submillimeter observations of T-Tauri star disks. So there may be an interesting question here as to whether observations are underestimating the disk mass. The alternative, of course, is the model is missing something, but as a theorist, you always point the finger at the observers first. And that actually has some, it's an interesting question that I think these guys will be looking at more carefully, because it's already acknowledged that the dust masses are based on a particular assumption about the mean dust size, that it's a millimeter. That's already much larger than the ISM dust size, and there's no real good constraint as to how big the dust grains really are on average. They could be larger, and in that case, the disk mass for a given amount of submillimeter emission would be larger. So again, these guys will all pretty much candidly tell you that the masses they have are lower bounds, because the dust size is probably not smaller than that, but they could be bigger. And then there's various other constraints too. If you look at the upper envelope of that m dot versus m object curve, the upper envelope of values in 1 million years would accrete about 1/10 of a solar mass. Okay, back of the envelope kind of calculation. Extrasolar systems, which have very massive planets, perhaps in those cases you need a bigger disk to form those planets. And recently there's a series of papers from Steve Desch, who is using chondrule formation constraints to argue that you need a more massive disk than the MMSN in order to have shocks to form the chondrules. Anyway, there's many different lines of argument that perhaps disk masses are larger than either the MMSN or the current submillimeter dust emission estimates. Now I want to show you in the last few slides what we did more recently, that yes, we actually added a viscous parameter, perhaps wisely or unwisely, but it's interesting to see the effect upon the gravitational torque-driven evolution when you add another source of angular momentum transport. So the simplest thing is to add the alpha viscous parameterization. So you add the viscous stress tensor and your viscous coefficient. So this is all that's new now. The coefficient is your alpha times the sound speed times the scale height. So this is a lot like your standard alpha model, except it is still non-axisymmetric. Okay, so it's not just rings rubbing against rings, it's fluctuations rubbing against fluctuations, and so the alpha is working in the azimuthal direction as well. And here's a kind of a basic bottom line result. If you put in alpha of, say, your canonical value of 10 to the minus 2, then the black lines show you how the solution differs from the red lines, which are what I showed you earlier for surface density, temperature, and the Q parameter. So notice that our beautiful self-regulated state is gone due to the additional term. You now can accrete a lot of matter in, and Q rises well above the critical value, particularly at late times. The surface density profile is spread out viscously. More matter goes in, but there's a tail of matter that goes to large radii. So the sharp edge is gone. And this is the case I mentioned earlier. Now when you lose the edge, you also lose the swing amplifier. And if I showed you a picture, it would be essentially an axisymmetric disk at this point. Okay, I won't mention much about the temperature. But that's, yeah, so basically we lose a lot of the nice features of this solution, of the self-regulated solution. What is the effective alpha for our models with or without the alpha viscosity? So let me point you to the solid line here. That's if you don't add any of this alpha viscosity on top of your model. That's your standard gravitational torque-driven model. You may ask, what is effective alpha for that? Well, there's many ways to measure that. This is the crudest, simplest way that we could think of to estimate an effective alpha, which is, well, you know, it's a global model, but you have to measure it somewhere, I suppose, or do some averaging. We chose to just measure the accretion of the inner sink and say, well, the rate at which matter's falling in is giving you some measure of, allowing you to compare with some smooth axisymmetric alpha model in which the steady state accretion rate would be given by this expression. And so we know what these quantities are in our model at the inner sink, and we know what that is. So we just pull out the effective alpha. So okay, so using that method of measurement, then in that late self-regulated phase, you're talking of something between, closer to 10 to the minus 3, but just below that. So what does that really mean? Well, it means that's why when I showed you the effect of adding an alpha of 10 to the minus 2 on top of our model, it dominated the physics. Because at least in the inner region, an effective alpha of the previous model was more like 10 to the minus 3. So in any case, it's not a game I'm very comfortable with, but it's that's an interesting way to understand why 10 to the minus 2 destroyed the features of the self-regulated state. But that leads to a larger question as to whether, is it even appropriate to be talking about effective alphas for gravitational instabilities or gravitational torque-driven evolution? Well, for the burst mode, the answer is clearly no. As again, many of you have pointed out in the literature, I mean, if you have a global mode, then by definition you don't have you can't use a local approximation. So for the first, call that the boundary between burst mode and self-regulated mode. If you look at the Fourier amplitudes of m equals 1 through 6, the m equals 1 and then the m equals 2 dominate in our disk. These lines, by the way, are smoothed out over time, over about 10 to the 4-year intervals, otherwise they'd be quite noisy. But the m equals 1 and 2 definitely dominate. You've got the global modes. It doesn't seem to me that you should even be trying to model the disk as some kind of viscous disk. However, in the later mode, where you've got the more diffuse spiral structure, well, in that mode, the m equals 1 and 2 are dominated by the higher order modes. And so now you've got a lot of higher order modes, and they interact with one another. There's a lot of net cancellation. By eye, it doesn't really look like a clear spiral. And you've got enough local fluctuations that perhaps you can think of this process as happening everywhere locally to some extent. Also, Q is being held at the critical value, roughly the same everywhere. So maybe one can get away with some kind of local approximation. And so in this state, I think if you wanted to model after 500 after 500,000 years, I think there is some scope for this. Lodato and Rice have studied, I think, what amounts to a similar situation where you don't have you have an isolated disk, no envelope feeding, and it showed very nicely that you can settle into a self-regulated state. In this case, as the spiral perturbations lead to enhanced heating and keep the instability from running away. So I think in this phase, one could go back to the Linen-Pringle prescription of a viscous disk, but not an alpha disk, right? That was a prescription where you had a viscous coefficient that was a function of the Q parameter itself in such a way, like it might go as 1 over Q squared, I think. So it would if Q got, so essentially it would drive the disk back toward Q equals 1, okay? So if you had some clever prescription like that, again, not an alpha disk, and in that case, I think you could model the late phase. The other advantage of a Q-dependent viscous parameter is that then the viscous parameter depends on the surface density, and that will help you to keep a sharp edge. As long as your diffusion constant is insensitive to surface density, you'll just smear out your disk. But if the diffusion coefficient itself is dependent on the surface density, then it's nonlinear diffusion, and you can have a diffusion front as opposed to instantaneous spreading of your object. Another way to see that, at least in an approximate way, diffusion is maybe some way to think of this late phase is if you take one of our models at 0.5 megayear and focus in on an annulus and then follow the evolution of the annulus at later times using tracer particles, then at a later time that annulus has spread out. Most of it's moved in, some has moved out. So again, you can think of that as kind of a diffusive process. Okay, so really these are my main points, and I'd say that what we're arguing on the basis of our modeling is that you conceptually can talk about an early burst phase where you have vigorous GI, you form clumps, and those clumps may be driven into the center and give you bursts. They may form other objects in a more general system. And the high points give you the effluori, and the low points may help explain the very low luminosity objects, which Spitzer is now observing. The bulk of the time, though, is spent in this self-regulated mode, which applies to the later time, but also approximately to the time between bursts in the early phase. And there you've got this essentially Q equals critical value, and you've got weak non-axis symmetry, which leads to torques that drive accretion in to the center. The actual numbers always depend on your initial conditions, so we're not in a position where we can predict, yes, that you always expect this many bursts, right? It's a function of the amount of mass and the angular momentum in your system, for example. And this is all under the assumption that there's no angular momentum loss from the system. I think in a more quantitatively accurate way, you have to account for losses due to magnetic fields, and things may be shrunken down to some extent. But we can get a range of accretion rates by different core masses initially. Interesting open question is whether the disk masses are either observationally underestimated or theoretically, do we need other processes to be occurring? And certainly other processes are occurring. And to what extent can those processes reduce the disk mass without necessarily destroying some of the other nice features of the solution? And so the alpha model, I think, doesn't do it in the right way, but other approaches may work. So that's basically this point. I think that's an open question as to what else is happening at the large radii, and certainly at small radii, we know that we need to fill in the rest of the story within 5 or 10 AU. Okay, thanks very much.
I was
Yes.
going to ask you what dependency was in your adiabatic index for your burst trace.
Okay, then the standard model, we do have a critical density of, 10 to the 11 or so per cubic centimeter. And then the index is 7/5, okay, 1.4. And we've experimented with that up to 5/3, 1.67.
And the burst phase stays when you've got 5/3.
It does,
It
it
must be,
does.
I mean, presumably
There's a lot fewer bursts. but
Okay, I'd
yes.
imagine. So if you take gamma to 1, you become violently unstable.
Yes, we've actually never tried that.
Will be isothermal.
Right, yeah.
So you still get, but they're more separated in time.
They are, yeah. Actually, let me see if I can. Yes. Okay. So this is an interesting slide. So this is our canonical model in the 2006 paper. I can't give you the exact numbers of the initial mass or angular momentum and so on. But if you start with some known quantity, that was gamma of 1.4, 7/5. If you go to 5/3, that becomes that. Okay. Still some bursts, but a lot fewer. But on the other hand, if you take this disk, you keep it at that gamma, but you add some more angular momentum, then that becomes that. Okay, so by increasing the mass or angular momentum, you get more bursts. So at this point, there's no unique predictability of number of bursts, except that it's pretty robust, I think. And as you get to the high end of the temperatures that people think might exist, you still get some bursts. Yes?
In a real disk with long cooling time, if Q falls less than 1, it'll heat itself up by turbulence. But it seems very different from your model where, because you have the adiabatic equation of state, if Q falls less than 1, it'll just accrete until Q gets back to 1. So it seems like it's a different...
It can be different, right? You can regulate Q through accretion in this model. There may also be the heating effect, right? Because, I mean, the heating is coming in through this barotropic equation of state. So
usually heating is much faster by h over r squared than accretion. So I'd expect the heating to be more effective, and that will shut off the accretion.
Okay, maybe so. Yeah, I couldn't comment. But it's true that we have two effects going on here. The accretion itself into the central sink is a big regulator of the evolution. Yes?
When you have your large-scale perturbations, they must be moving very supersonically at some point with respect to the flow. What is the typical Mach number?
Oh, sorry, I don't understand. Which?
You have your large-scale spirals
the flow.
moving through the background flow. They might be very supersonic.
Actually, you mean the clumps moving through, right?
Or even the spiral.
Okay. Yeah, actually, we may have missed a few, but I haven't seen any strong indications of strong shock fronts. They may exist.
Since they extend over a range which is
Yeah.
much larger than H, really,
Right. Yeah.
they must be supersonic in some.
Yeah.
Some parts.
Okay. That may be. Yeah. And we do have artificial viscosity to spread it out.
You have artificial viscosity.
Yes. So, yeah, I'll leave it there. Yeah.
Yeah, related to that, the clumps seem to fall in very fast. Are they falling in supersonically also? Or?
They probably are, but I can't give you a number.
Because you know that the orbital period where they form is probably a few hundred years, or maybe a few hundred years, a few thousand years, and they seem to fall in almost faster than that.
Well, I think it is comparable to the orbit period, actually.
But even that is extremely fast.
Right, yeah. So I don't know if it's, the key question as you have, it's always a matter of how fast the gas is moving relative to the neighboring gas, right? And whether or not that's enough to form a shock is still open question, I think. Before you form a disk, you have extremely supersonic inflows, but you have no shock because there's not a relative motion of mass shells that's supersonic. Okay. Yes.
You're speaking about the outer edges. Where is it approximately at that outer edge? Does it?
It moves outward over time, so it could be 50 AU at some point. For these, again depends how much angular momentum you have. So in this model, look at the red. It's at about 50 AU at 0.2 megayears, and then it moves out to about 100 AU.
What time?
In the course of 2 million years. So you build it up to, you initially build up a disk rather quickly, typically to tens of AUs, and then it spreads out to 100 or hundreds of AU in this model.
It is pretty robust actually, again with the or realistic parameter ratio. You cannot change it.
Well, I mean, again, canonically, if you calculate a canonical centrifugal radius, you get something like 100 AU based on the angular momentum in a typical prestellar core. That number, however, is quite sensitive to the amount of angular momentum, which is the high power of the angular velocity. So it is true that small variations in the input angular velocity of your prestellar core can make a big difference in the final size of your disk. There is a
But
sensitivity
basically,
there.
it's just a standard estimate. I mean, you equate the things, you determine the radius, right? Nothing else.
Right, yeah. We're not, it's self-consistently forming, yeah. And the initial radius is, yeah, something similar to estimates you might make based on the angular momentum that was in the prestellar core. Yes.
Yeah, so I mean, I understand there's no radiative transfer, so I'm wondering how you chose the temperature normalization, because I would have guessed that disks that are accreting at such high rates would heat up above 40 degrees Kelvin.
Mm-hmm. Yeah, I think the temperature estimates we have observationally are no more than maybe 20 degrees above what we have at the highest end, so in our standard model. And so then when we mid-plane temperatures, I think, if I understood correctly. I could be wrong on that. So, I mean, our calculation is certainly giving you the mid-plane temperature. So when we go to the higher gamma models, we are bracketing the observed inferred temperatures. Okay. Beyond that, I mean, when we've got the clumps, we are in the adiabatic regime of our barotropic equation of state. So there is quite a bit of heating going on at that stage.
Yeah, I guess I'm just wondering if those temperatures are consistent with the energy about the release power decrease.
Right. Yeah. Well, that's a good thing to check. Yeah.
I guess on a similar note, what's observed is perfectly right. You've got an optical depth of 10 AU of 100 or something. So
Yeah.
they're seeing 60 Kelvin there. You should be measuring something greater than that. Maybe not significantly greater, but somewhat greater.
Okay. Right.
I was trying to look in my head. I can't quite do it. Fourth of a towel.
Yeah. No, it's a good constraint. But yeah, I mean, basically, yeah, if you're 10 times MMSN at 10 AU, then does that have some? Is that ruled out by the observations or not? Yeah. I'm
So
not
often
sure.
the mid-plane temperature, that's really out because you're seeing the photospheric, the disk surface really not the mid-plane.
Right. Yeah. No, good suggestion. Okay, other questions? Yes.
Would you be able to adapt your numerical method to include heating and cooling, I mean, to capture the heat generated by the gravitational?
I think so. Yeah. Why not? I mean, we can have an energy equation, and
Yeah, because
yeah.
as Joran points
Yeah.
out, it
Right.
could lead to a different form of
Right.
self-regulation.
right. Yeah. No, it's true, and we are actually pressing ahead on several of these fronts. So let me show you. You know, there's a whole laundry list, of course, of things you can put in, and I think in principle, most of these effects could be put in. Actually, Edward is working on the heating and cooling, and we're working on the magnetic braking and ambipolar diffusion. So, I mean, I think over time we will fill in the space, and yeah, I think there's no reason why you can't do an energy equation. And that is probably the next step. Okay. All right.
Okay, so now next week, of course, we have the workshop on planetesimal formation from Monday till Wednesday. So we won't have any other talks. It'll be quite enough. And then for the following week, if anyone would like to suggest a talk or a discussion topic, then do let one of the organisers. So let's go and have some tea now. Thank you again, Shantanu.